Hello, my name is Vladimir Matias and I'm from iBeam Materials in Santa Fe, New Mexico. It's a pleasure to be here today at SVC TechCon 2021. The title of my talk is IonBeam Crystalline Templates for Roll-to-Roll Manufacturing of High-Temperature Superconductor Tapes. I would first like to acknowledge my collaborators in this work at iBeam Materials. That's Chris Sheehan, David Best, and Klaus Kunze. At Sandia National Lab, the team led by Paul Clem helped us to develop the solution deposition planarization process. At Los Alamos National Lab, Terry Holzinger did some of the key microscopy work on our materials. And at Stanford University, Dr. Robert Hammond was the inventor of the IBAD texturing process and a friend and collaborator for a long time. Here's an outline of my talk. I'll give a brief introduction to IonBeam assisted deposition or IBAD texturing. I'll discuss IBAD-MgO scaling and what we've demonstrated so far. And then I will discuss the HDS template architecture and remaining challenges, and I'll summarize at the end. IonBeam assisted deposition, or IBAD, is a process that is widely used in industry for a variety of effects. However, we are doing something very specific, which is texturing or crystal alignment, and that occurs in a very narrow region of phase space. IBAD texturing or crystal alignment induces texture in the film during deposition. The schematic on the upper left shows what happens when one deposits a material on a polycrystalline or amorphous substrate. One typically gets randomly oriented grains or a polycrystalline film. On the bottom we see what happens under very specific conditions if one has an ion beam during deposition, which is off-axis. One can get in-plane and out-of-plane or biaxial crystal alignment in the film. The particular version of this IBAD texturing that we utilize was discovered in the mid-90s at Stanford University by Bob Hammond and colleagues. The process requires a very thin deposit, typically less than 5 nanometers. So it occurs in the very early stages of film nucleation and growth. We have demonstrated that the process can be done in less than 1 second. So one can flash the deposition with an ion beam very briefly and then move on to the next step in the deposition, making the process extremely high throughput and very low cost. So how does IBAD change epitaxy? Well, instead of using a single crystal wafer for epitaxial deposition, one can now eliminate that single crystal substrate and use an arbitrary substrate and then deposit a single crystal-like layer on top of that substrate and thereby create a template for epitaxy. So this enables one to utilize a range of different substrates that have desired mechanical and thermal properties, but are free of the requirements of lattice matching that typically come with epitaxy. But more importantly, one enables large area, low-cost substrates such as glass, metal foil, and others, and one can do extremely large deposition, including roll-to-roll. So IBAD templates really are a new paradigm for epitaxial deposition that enable large area epitaxy. IBAD is a physical vapor deposition process where one deposits a material in a vacuum system while an ion beam impinges on the sample, as shown in the figure on the left. Typically, we use a in situ monitor such as Read to determine the crystalline orientation during deposition. On the right, you see a schematic of our reel-to-reel system at iBeam Materials, where we have the ability to move the sample between different deposition zones and thereby combine different materials and deposition methods with the IBAD process. The science behind the IBAD texturing process is still poorly understood, but we have a lot of data on how the texturing occurs. IBAD texture evolution for MgO is shown here in the figure. The y-axis shows in-plane mosaic spread, and the bottom axis shows the total film thickness, both on a log plot. One can identify 3 regions during deposition and how the crystalline alignment occurs. On the top here I show the read diffraction images from each of the regions. In region 1 of the figure, at initial MgO deposition during IBAD, there is an amorphous layer of MgO formed on the surface. And then at about 1 to 2 nanometers of deposit, crystallization occurs, i.e. a first-order phase transition. From then on, under IBAD, texture improves. This is what I call the 2D region of grain growth and coalescence. There is an optimum point at which texture no longer improves under IBAD, and it is important to stop IBAD at this point as the crystallinity will only degrade. However, the texture improves further by 3D growth in doing homoepitaxial deposition without an ion beam or epitaxial deposition of other overlayers. That is in region 3. The ultimate alignment that can be attained is a function of optimizing all these steps during deposition process. I want to focus briefly on 2 topics regarding the IBAD-MgO process. The first one concerns how fast can the IBAD texturing be. Early on, it was recognized that a key parameter for IBAD texturing is the ion-to-atom ratio. And the question is whether we can attain the same level of alignment, crystalline alignment, by scaling the deposition rate and ion flux together. The answer is yes, at least the first order. The graph here shows the texture evolution for in-plane texture for a series of different deposition rates as a function of IBAD time. So what it means is that we can achieve very short deposition times by going to high deposition rates while increasing the ion beam flux at the same time. Ultimately, we're limited only by how much ion beam flux we can have from our ion source. The data point here corresponds to less than 1 second of deposition time, or a throughput speed of 540 meters per hour for the 12 centimeter deposition zone that we use in our system. The movie in the right top corner shows how fast the reel is moving at this speed. However, I want to emphasize that this is not an absolute limit on the speed. It is determined by the length of the deposition zone in our system. So by going to a longer deposition zone, one can get a higher throughput speed. The second issue I want to focus on is how well can the MgO layer be aligned. As I said before, this depends on a lot of factors, but we have found that we can empirically characterize the evolution and from this extrapolate what is attainable. Here I show the texture evolution of MgO in the region 3 of homoepi deposition without the ion beam, and how it improves with thickness. In this case, we show the in-plane alignment of less than 1.5 degrees for thick MgO layers. The actual value will depend on the IBAD process step as well as the substrate roughness and other parameters. In the final epitaxial overlayers, we have seen in-plane spreads of even down to 0.5 degree. IBAD has enabled long lengths of high-temperature superconductor wire. In particular, the fast IBAD-MgO process has been the preferred one for most manufacturers because of the high throughput and high quality. I will not talk about the HDS wire much, but there are other talks in this session on this topic. I believe that HDS on IBAD is one of the largest applications of epitaxy in the world today. There are about a dozen companies making a total of about 1,000 kilometers of wire per year today. Shown here is the schematic of the IBAD template structure for HDS. We start with a planarization layer, which provides a barrier layer and a smooth surface for the IBAD deposition. We call this solution deposition planarization, or SDP, which is essentially a chemical solution deposition process done in air. Following that, we deposit IBAD and other epitaxial buffer layers by PVD. And then the HDS layer is deposited by a variety of possible methods. At our company, we do not deposit HDS, but we work with partners who have their own deposition methods. SDP is essentially a sol gel process whereby one deposits a liquid solution layer by surface tension very smooth, and then by converting it to a solid, it retains some of the original roughness. But by doing multiple coatings, one gets a progressively smoother surface. In this way, we can achieve any desired smoothness that we need to attain. The typical roughnesses that we start with are between 10 and 30 nanometers on a 5x5 micron scale. The substrate AFM image is shown on the top right and after planarization on the bottom. Typically, we get less than 1 nanometer after planarization. We use a Hastelloy metal foil. More recently, we have been successful in reducing the number of coatings needed to get to the less than 1 nanometer roughness, and in some cases less than 5 coatings, depending on the starting substrate roughness. We have also verified that the carbon content in these films is very low, less than 1%, by doing the conversion process properly. One of the particular benefits of SDP is the ability to block out defects in the substrate. On the left, you see a TEM cross-sectional image of some porosity in the substrate, and on the right, a particulate which is on the substrate surface. In both cases, the SDP layers cover up these defects. And these types of defects are more challenging for other planarization alternatives such as electropolishing. Ultimately, we need the crystalline alignment to transfer from the IBAD to the HDS layer, in this case REBCO. On the right, you see how the in-plane texture improves through the template stack. Typically, we start with an MgO layer of about 4 to 5 degrees of in-plane alignment, and by the time it gets to the REBCO, it is about 2 to 3 degrees of in-plane alignment. This is sufficient alignment to obtain critical currents as high as that of epitaxial films on single crystal substrates. There has been a lot of success in HDS wire development over the last couple of decades, but the key remaining issue is still cost reduction. This can be done, of course, in 2 ways, by improving the HDS performance and reducing the manufacturing cost. For the manufacturing cost, it is important to have high production throughput and scale up the process. As far as the IBAD template is concerned, as we already showed, the process is extremely fast, meaning very low cost, a small fraction of the total cost of the wire. The main remaining challenge for IBAD is to scale up to wider webs that would be needed for HDS deposition. So far, industry has been confined to half-inch wide deposition, and it is time to scale up to wider webs. In summary, let me just say that IBAD has enabled long lengths of epitaxial superconductors for HDS wire. Today's HDS epi films on IBAD are as good as on single crystal substrates. And for the future, we believe that scaling to wider webs will be important for further HDS cost reduction. Thank you.